Myself Monica Rajkumar, and this is my advanced UAS mapping course project during fall 2021. Today we will be discussing my research on automating the volume computation process from the UAS Imagery. This research project was sponsored by Bureau of Land Management, and I would like to thank the contributors Dr. Sitagar Nagarajan, Dr. Hongbo Su, and Peter DeWitt, who is the land manager of the study area chosen. And further, I extend my gratitude to the Florida Atlantic University. Presentation today will cover the background on the research performed on the ONA, the objective of the research we performed on the ONA, a short look at how we collected and processed the UAS data for analysis, and the methodology we performed to obtain the solution for the problem that we have, and the outcome of the research performed on the ONA, which will be further followed by the future scope of the project. Coastal erosion is the loss or displacement of land along the coastline due to the action of waves, currents, tides, wind-driven water, waterborne ice, or other impacts of storms. In Florida, we have a lot of storms and the possibility of hurricane, so coastal erosion is a direct result of that. In this image here, you can clearly see that the original profile of this portion of shoreline is everything intact, followed by the storm profile that shows the storm water uh, above the high tide and low tide, which generates an erosion escarpment where the original frontal dune and incipient dune are located. After the storm event, we can clearly see that the seaward we have lost a significant portion of shoreline, some of which included the frontal dune and the incipient dune. This is why computing the volume change of the shore is necessary. Over time, the shoreline of the Jupiter ONA has receded significantly, and hence capturing it frequently and thereby computing the volume change of the soil is a vital process. Being complex and dynamic, shoreline reflects the natural processes like erosion and deposition. Since the traditional methods on computation, the volume change is going to take more man hours, automation of this process is important. Here we have our study area, which is located in Jupiter, Florida, with the Indian River bounding our shoreline of interest to the east and the Loxahatchee River bounding our shoreline of interest to the south. The Jupiter Inlet Lighthouse ONA, which is the outstanding natural area, our shoreline to the north. More particularly, the area of interest is highlighted in red over here. So here, when we see the shoreline, so here is where we are going to take a subset of the area and then try to compute the volume change in that particular region. Elaborating on the significance of the study area, there is an impressive number of species living in the ONA. From the most recent BLM report, the ONA is home to over 700 species, out of which 28 are considered to be the special status species. Apart from that, the ONA receives an average of 100,000 visitors per year. So if no one takes care of or monitor the loss of shoreline and loss of erosion, as evidenced by the map shown previously, there will be no ONA to visit, to inhabit, or to enjoy. Florida Atlantic University has been working on this site for the last several years, mostly on the archaeological investigations, and we performed shoreline change detection, volume change computation along the shore region, and we also performed vegetation classification using machine and deep learning techniques. Whenever needed, we usually compute the volume change manually, which is going to take more man hours absolutely. That is where we have been motivated to automate the process of volume change computation for any given region. Firstly, I just wanted to introduce certain terms which is needed for this project. That is coastline and shoreline. Shoreline is the line where the beach ends and the land starts, and coastline, which is otherwise called waterline, um, is the line where the water body and the shore region meets. Shoreline is being used very often to perform the computation of volume change. So, on automating this computation of volume change will reduce the human intervention, and it can also be extended to more Bureau of Land Management areas or sites in the future. The primary goal of this project is to check whether the high resolution UAS imagery can be used for the volume change detection and computation for two different data collected from April 2021 and August 2021. The table here clearly shows the specification of red edge mica sense camera used for the data collection for this project, and it actually consists of 5 bands, namely blue, green, red edge, and near infrared. The wavelength information of each spectral band is shown here for the mica sense camera sensor. As you can see here, data was collected separately for two different regions in the Jupiter Inlet Lighthouse ONA during the months of August 2021 and April 2021. These are some of the notable advantages of UAS, which is a low cost device, and it uses ultra high spatial resolution, and it has enhanced temporal resolution, and it takes very less time for surveying, and it even allows us to inaccessible areas, and it's used in various other monitoring and development process. So the raw data acquired from the drone was then processed using Pix4D mapper and 3D point cloud products, digital elevation models, and the orthomosaics were all produced from the drone processing using this particular software. So this is the overall methodology that has been adapted for the research. It's like first we process the raw data using the Pix4D software, and then we generate the orthomosaics, DTM, DEM from Pix4D, and then we extract the shoreline and coastline, which is used to prepare the data for unnecessary features. Like for example, in a particular region, we'll be having some stones, or some vegetation features or something like that. So we have to remove those features from the volume computation, like volume change computation. So those data has to be prepared as a polygon data. So that is being collected, and then we create a polygon based on the shoreline, coastline, and the unnecessary features. So overall now we'll be having a polygon with us. With the help of this polygon, we'll be clipping the DTM of April and August 2021 data. So we have two DTMs now. These two DTM will be subjected to raster calculator to find the difference of those raster. This particular output raster is helpful in computing the volume change of that particular data. Finally, we'll be changing the volume to cubic yards and save the results as CSV. So once all these processes been created as a geoprocessing tool, finally we have to remove all the intermediate results that we have for this tool. So now we can go to the results at each step in the upcoming slides. For instance, let's assume a small area, like a particular region, to compute the volume change. Here you can see the orthomosaics of August 2021 and April 2021. So we are just now going to consider this particular area for the volume change, and we are going to remove all these manually added stone beds. Here you can see the DTMs of August and April data, and as you can see here, you can see the values of the the stone beds, which is clearly seen, and here it's not there, so because it's from April data. So we now have all the input data. Let's see how to compute the volume change, like how to automate the process. So I use the ArcPy module to build a geoprocessing tool in the ArcGIS Pro, which can be further extended to develop a task workflow. So this is the developed geoprocessing tool for the volume computation, which takes the shoreline and the waterline as input, along with the areas to be clipped, like as I shown the artificial stone beds. So those are all the areas to be clipped, and 2 DTMs of April and August. So these are all the inputs. With the help of this, we will get the output as shown here. So as you can see in the left image, we see the shoreline in red and waterline in blue, and the areas to be removed in black. Now, using the DTM we are clipping that particular region to compute the volume. So having the raster, we use the surface volume tool to generate the volume in feet, and then we convert the volume to cubic yards. So this is the generated result for this particular region. Similarly, we can do for any given region by giving the shoreline, coastline and the areas to be clipped as input. So the advantage of this project is it reduced the man hours in volume change computation, but the limitation is we also need some mandatory inputs which has to be prepared. For example, the areas to be clipped has to be prepared. So in future we have to plan that to deduct all those stone beds automatically and to remove those portions without any human intervention. So the future scope is we have to perform the volume change for several years, because currently we do only for 2 particular data, like any 2 years we can take and do that. But in future we have to do for several years, and we also plan to adapt this workflow for a larger study area. So these are some of the references that has been used for the purpose of this project. I'd like to thank Bureau of Land Management for their support in collecting the data, and also extend my gratitude to the Florida Atlantic University, especially the Department of Civil, Environmental and Geomatics Engineering, along with the Advanced Geomatics Engineering Lab. Please let me know if you have any questions for me. You can always email me. I thank everyone for all your patience.